All right, we'll get started then, and hope you guys are all doing well. It's week 10, very last week of instruction, and so I guess kind of the last topic we have to cover will be hypothesis testing for means with two samples, and we'll cover this, and then Wednesday and Friday we'll spend in review for the final exam. So this is our last topic. For two samples, okay? So, I mean, so far we've covered, just kind of, so far, we have covered, okay, we've got confidence intervals for P, confidence interval for mu, confidence interval for mu1 minus mu2, okay? We've also covered hypothesis testing for P. This is we also did hypothesis testing for P1 and P2. We've done hypothesis testing for mu, and then today we will do hypothesis testing for mu1 and mu2. Okay. The only thing in the pattern that we did not cover was confidence intervals for P1 minus P2. It's on that formula sheet, but we did not cover it. I think it's chapter 7, section 5 in the textbook, if you're curious. But I feel like it's okay that we didn't cover it. All right, I'm not going to put it on the final exam. You don't have to worry about that. So, okay. I hope no one's heartbroken about that. Okay, so this is what we'll cover, and so this is what we got. Okay, hypothesis testing for means two samples. Again, the big idea here is we are looking at two samples. Okay, we observe two samples, and it's a numeric variable. Okay, and based on the sample means, can we then conclude that the respective populations have different means? You will see a lot of parallels between the hypothesis test for means two samples and the confidence interval for mu1 versus mu2. They're pretty much the same, except just you're looking at the same problem from two perspectives. So one is, with the confidence interval, you are trying to make a range of plausible values of the quantity mu1 versus mu2, mu1 minus mu2. And then with hypothesis testing, we're just testing out whether 0 is, if we've got evidence that mu1 minus mu2 is 0 or not, okay? But the math and everything, it kind of works out the same. Whatever conclusion you make from a hypothesis test, that conclusion will match the conclusion from a confidence interval, okay? I'll say very similar. So okay, well let me So the process is very similar to hypothesis test for P1 and P2, but the conclusions will be identical to confidence interval for mu1 minus mu2. Okay, so the conclusions for a hypothesis test with two samples will be the same conclusion for a confidence interval for mu1 minus mu2. Okay, so if the confidence interval says we have evidence of a difference, then your hypothesis test will also say we have evidence of a difference. Okay, all right. So let's we'll go through the process. We'll talk about, we'll do some examples, and then we'll talk about some of the finer points here. Okay, so the first step in all of these things is set up your hypotheses, right? Okay, the null hypothesis in this case will always be mu1 is equal to mu2, which can also be written as mu1 minus mu2 is equal to 0. Okay, both of these null hypotheses are equivalent. They say the exact same thing. Then the alternative is mu1 does not equal mu2, okay? Or mu1 minus mu2 does not equal 0, okay? Or you can have greater than 0 or less than 0, okay? Or mu1 is greater than mu2, or mu1 is less than mu2. Null hypothesis would be that the population parameters, population means are the same for both populations, or that they're not. Okay. Then we check our conditions, right? Check conditions, pick alpha. Step 3, this is where we do all our calculations. So with our calculations, we'll start off by finding the standard error. The standard error is going to be the square root s1 squared over n1 plus s2 squared over n2. Then you get your test statistic t. Okay. Our test statistic t is going to be x bar 1 minus x bar 2. It's the observed difference that we got. We're going to say, is that difference big or small compared to the standard error? Okay. And then once you get your test statistic, we look up t in the t-table to get a tail area, and then a p-value. Okay. So when you go to the t-table, you need your degrees of freedom. Our degrees of freedom will be what? N minus 1, but we have two n's, so use the smaller value of n1 and n2. Okay. And then this part is the same as using the t-table from before. So what do we do? If the alternative has a greater than sign, what? Our p-value is equal to the right tail probability. If the alternative has a less than sign, then the p-value is equal to the what? Left tail probability, or tail area. And then if the alternative has a not equal sign, then the p-value is 2 times the tail. All right. So I think this part's okay. Again, all of these formulas are written on your formula sheet, which is going to be part of the final exam. So as long as you've got the concepts, then everything should be okay. Okay, and then the last part, make our conclusion. Okay, so make our conclusion, and we will do if the p-value is greater than alpha, this means we do not reject the null. And we would say we do not have evidence that mu1 is different from mu2. Or, is greater than or is less than. Okay. Depending on what the alternative says, right? All right, and on the other hand, if the p-value is less than alpha, we do reject the null hypothesis. And we say we do have evidence that support the alternative hypothesis, whatever the alternative says. Okay, I'm hoping this is good with everybody. All right, so let's do an example here. Okay, so we'll say does, or I don't know. Okay. Does what? Name brand garbage bags, I guess do name brand garbage bags hold more than generic or store brand garbage bags? Okay, it's an important question. Okay. All right, so somehow, you buy the name brand. What's the name brand for garbage bags? Glad? Okay, so you buy Glad garbage. Okay, Glad trash bags, and I don't know, you load them up with, you do some kind of experiment, materials engineering, okay, and you throw in a bunch of, what do you put in a trash bag here to test its strength? Okay, so you load it up with heavy things, and you test when the bag breaks. Okay, you buy Glad trash bags, and then you test when they break. All right, let's see what happens. Okay, and we'll say you did I don't know, 15 random trials. The average breaking weight, I don't know, how much do those trash bags hold? Okay, was 60 pounds, okay? And there's the standard deviation is, I don't know, 4.5 pounds, okay. 60 pounds of trash, maybe. All right, and then you buy, you do the same thing with the store brand. Okay, oh, no, question mark, store brand. Okay, and then so we'll do another 15 random trials. And we'll say average breaking weight is 57 pounds with a standard deviation of 3 pounds. Okay. All right, so does our data provide evidence that name brand, so we'll say that the Glad bags are stronger? Okay. Yeah, let's somehow make this a clicker question, except I got to figure out some fake answer choices here. Okay. Okay, so we'll say options for your p-value: A, B, C, D, and E. And this is pretty close. 501.025. Okay, so we'll say okay, we'll see these are your p-value choices. So even though the question says, does our data provide evidence that Glad bags are stronger, we'll just say find your p-value. Okay, so go ahead and try that out. I'll pause the video here. Okay, so we'll go over our answers. And let's see. Okay, so when we set up our hypotheses, the first thing we're going to do is basically our hypothesis will be that the two bags have the same strength. So we'll say mu1 is equal to mu2. We'll call mu1 strength for Glad, and then the other one will be strength of store brand. Okay, so this will be our null hypothesis. I can also write mu1 minus mu2 is equal to 0. That's also fine. Okay, and then our alternative, we want to the question was asking, do we have evidence that the store brand is stronger? So we want mu1 is greater than mu2. I mean, not store brand, that the name brand Glad was stronger than the store brand. So we want mu1 is greater than mu2. Okay, or we can also write mu1 minus mu2 is greater than 0. All right, then we go through and we set up our standard error. our standard error is S1 squared over N1 plus S2 squared over N2, right? So S1 is 4.5. We're going to square that. We divide that by the size of our first sample, 15. The other one, 3 squared, we divide that by the size of that sample, which was 15. When I do these calculations, I get some number here. Okay, so I'll do 4.5 squared divided by 15 plus 3 squared divided by 15. Okay, well, 1.3964. Okay. My test statistic is going to be x bar 1 minus x bar 2 divided by my standard error. Okay. When I looked at the problem, the average strength when the glad bag broke was 60 pounds. We're going to subtract off the store brand 57, and then we'll divide this by 1.39642. So in here I'll do 60 minus 57, and then I'm going to do divided by answer. Okay, that way I don't even have to worry about retyping all of this in. Okay, when I get this, I get 2.1483. All right, so we'll go to our t-table. T-table, how many degrees of freedom do we have? 14 degrees of freedom, right? Degrees of freedom is equal to n minus 1. Both of our n's are 15, so it doesn't matter. We've got degrees of freedom equal to 15 minus 1, 14 degrees of freedom. So we come here, we go to 14 degrees of freedom, and we're looking for the number 2.148. So that's very close to here. This is 2.145. We're at 2.148, so we're somewhere in between 0.025 and 0.010. Probably very close to 0.025, but a little bit less than that. So my right tail is between 0.025 and 0.01. Okay, that's what I have here. My alternative has a greater than sign. Therefore, my p-value is the right tail. So p-value is equal to the right tail. And so my p-value is between 0.025, which is greater than my p-value, which is greater than 0.01. So I believe that answer choice matches answer choice B here. Okay. If you doubled it, you would have gotten E, but we don't double our answer choice because the alternative has a greater than sign. So my p-value is between 1 and 2.5%. If alpha is equal to 5%, then we reject the null hypothesis, and we say we have evidence that the name brand trash bag is stronger than the store brand. So maybe it's worth the extra 25 cents or not, but who knows? Okay. All right, is that good? Yes, question.
What if you had switched mu1 and mu2?
What if you had switched mu1 and mu2? Okay, so what would happen in that case? So if you had switched them, you would come to the exact same conclusion. In that case, your test statistic, okay, so this is a good question. You know, if I had switched, okay, so if we switched the labels group 1 and group 2, Okay, my standard error would be the same. Okay, because if we look at the standard error, basically this thing would be over here and this thing would be over here, but because you're adding them together and they're inside the square root, that number is going to be the same. What will happen is that my test statistic t would change. Okay, my t would become 57 minus 60 divided by the standard error. And so my test statistic would end up being negative 2.1483 or whatever it was. Yeah. And so in this case, oh, and the other thing that would also change is that my alternative hypothesis would be that mu1 is less than mu2, okay? Or that mu1 minus mu2 is less than 0, okay? So in this case, my alternative hypothesis changes, and my test statistic becomes negative of the other, okay? And so, so in this case, when I look up, we look up t in the table, okay? And what happens now is we change the top to left tail probability, right? We're looking up negative signs, and we have now the left tail probability, and then we're going to look at the same values. So instead of right tail, we now have left tail probability. We still get the same thing, and we still get our left tail is between 0.025 and 0.01, okay? Our left tail is between 0.025 and 0.01. Okay, and so in this case, because the alternative now has a less than sign, my p-value is the left tail. Is the left tail, and therefore the p-value is still between 0.025 and 0.01. Okay. So if you had just switched the group labels, your resulting p-value and thus your resulting conclusion will not change, because switching the group labels will switch the sign in your alternative hypothesis, and when you switch the sign in your alternative hypothesis, you'll be looking at the left tail. Switching will also change your test statistic to a negative value, and thus when you look that up, you're looking at the left tail and your p-value ends up being the same. All right, is that okay? This, I don't want to confuse anybody here, okay? Was that explanation okay, or do I need to go further? Yeah, another question.
How are you supposed to look up the negative?
How do you look up the negative t-score? Basically, you just say in your head, oh, I had a negative sign here, okay? But when you look it up in the table, you just ignore the negative sign, okay? But the fact that your thing was negative just means you change this from right to left, okay? So it doesn't, you got negative 2.148, you're just looking up 2.148, okay? You still end up in between these two columns. The only thing that changes is that now instead of the right tail, you're dealing with the left tail, okay? All right, is everyone okay with this? Okay, I'm going to bring this up, okay? And, okay, I don't want to confuse anybody here, but I'm going to do this, okay? What if our question was, are name brand bags weaker than store brand? Okay. What if we did that? What would happen now? What is my alternative? My null hypothesis is still the same, right? It's that they have the same strength. The alternative here, okay, we're going to call name brand group 1, and store brand will be group 2, okay? My alternative will be mu1 is less than mu2. Is that okay? But what does my data show? My data shows that the name brand bag, X bar 1, was 60, and that the store brand was 57. Okay? So before we even do any math, okay, what's the answer to our question? Are name brand bags weaker than store brand? Does our data support that notion at all? It doesn't, right? It goes like, we can just go with common sense here and just say, well, when I did my experiment, the store brand bags were stronger, right? So if the question is, I keep getting these messed up. When I did my experiment, the name brand bags were stronger than the store brand, okay? When I did my experiment, the name brand bags were stronger. So if the question is, do we have evidence that the name brand bags are weaker? The answer is no. We're not going to have any evidence, okay? But we could say, well, I insist. Let's do the math to check this out, okay? Well, we do the math. We're going to end up getting our same test statistic as before. 60 minus 57 divided by the standard error. We get positive 2.1483, okay? We get this value from before. And so now we end up with a slightly strange situation here, okay? We look up t equal to positive 2.1483, and what that tells me is that my right tail probability is between 0.025 and 0.01, okay? This is the same as before, right? My right tail probability, when I look up t equal to 2.1483, we get that the right tail is between 0.025 and 0.01. Okay. And this is where the slight change happens, or I don't know. Okay, is that our alternative has a less than sign though. Okay, this means we take our p-value is equal to the left tail, right? P-value is equal to the left tail. That's what the less than sign means, right? So what do I do here? I know my right tail is between 0.025 and 0.01, but this time I need my p-value to be the left tail. Okay? So we have to do, what we know is that the left plus the right equals 1. Therefore, my left tail is 1 minus basically the range 0.025 to 0.01. Okay? So therefore, my left tail is between 0.975 and 0.99. Which is kind of silly, but that is the technical answer here. Because if someone says, are name brand bags weaker than store brand bags, and you do your experiment, and if anything, it appears that the name brand bags are stronger, then we will not have any evidence to support this alternative, right? So we have no evidence, or we do not have evidence to support the alternative. I would say this doesn't happen as often because generally, as soon as you check your data, you should say, oh, well, that was a disappointment. I don't have any evidence to support this, right? It would be like someone says, someone claims like you take, I don't know, let's say you're applying for law school, right? And then you walk around campus, there's all these LSAT ads, and it says that, take this LSAT class and, your scores go up, right? And then, you want to know, well, do these classes actually work? You know, if I go and I take the class, will the scores go up, right? What you're hoping for is that people who before, the scores before are lower than the scores after, right? Let's say you did an experiment and then you had the before and then you did the after, and like the after scores were lower than the before, okay? You would not advertise that. You would not say, oh, look what happened. After they took the class, their scores were lower. That would be a terrible class, and you would not bother doing a statistical test to see if these classes are helping. Okay, so generally, you know, as soon as you see the data and you see like it doesn't align with your alternative, you can just stop there and say I don't have any evidence. But if you insisted on going through the process, you would have to kind of do this 1 minus stuff business. But I would say that's less so the case. Okay, is that good? All right. Let me just give you a few pointers here. I have the practice final. I don't know if you guys have taken a look at that already or not. I would recommend this week. Well, I know you got a lot of classes to study for, so you know, as your schedule allows, take a look at the practice final. And one of the key things is being able to identify which problem am I dealing with, okay? You've got to be able to tell, right? I listed off like 7 different scenarios, right? You got to be able to know, am I dealing with confidence intervals versus a hypothesis test? Am I dealing with proportions versus means? Okay, and do I have 1 sample versus 2? Okay, you've got to identify all of these things first, okay? Figure this out first, and then deal with the problem, okay? If you get this part wrong, if the problem is hypothesis test for means with 2 samples, and you conclude that it's a hypothesis test for proportions with 2 samples, everything you do there from there on out will be wrong, okay? Because the way you analyze proportions versus means, very different, okay? Or if you think you're dealing with a confidence interval when in reality it's a hypothesis test, again, you're looking at trouble, okay? Or you know, if you get any of these things mixed up, it's going to mess up the question. And each question, you know, the way the final is laid out is very similar to the practice final. I describe a scenario with some data, and then I'll have maybe 3 or 4 questions related to that scenario, okay? So if you get the identification of what type of problem it is wrong, that's like 3 or 4 questions that are going to get messed up, okay? Generally, you know, if you get the identification correct, then you'll get, you might miss 1 of those questions, but you know, most everything else will be fine, okay? But this is super important, okay? And I think the most common mix-up is proportions versus means, okay? So how do we know proportions versus means? Okay, proportions. This will be, the problem is a categorical variable. Okay, so as you're reading, you got to ask yourself, is this thing that's being described, is it a categorical variable? Okay, so you have to imagine, you know, taking the measurement, and am I writing down a category, or am I writing down a numeric variable? Okay, proportions will be categorical variables. If you still can't figure out whether you're dealing with proportions or not, things that you'll want to look for. The data is given as counts. So it'll be something like, you know, your sample was, you know, 250 M&Ms, and you have 45 blue M&Ms, okay? All right. In this case, your data is provided as a count. This is a count. Okay, so data is given as counts. I mean, the data could also be given directly as a proportion, right? Or given as counts or a proportion. In that case, I think it would be very clear that you're dealing with a proportion, right? If the problem says the proportion of blue is, 20%, is 0.19. I hope this will be clear that it's a proportion, okay? But inevitably, someone messes this up, and it makes me sad. Okay, so that will be clear. I hope, and obviously, if you see the word proportion in there, that's a good indication. As far as means go, it's just the opposite. You're dealing with a numeric variable. Okay. So a few hints or some things to look for. If you see units, okay, units will generally be an indication of a numeric variable. So if it says something like 32.5 pounds, okay, the fact that it's measured in pounds is going to be numeric, right? Or the dollar, it could be $15.50, okay? Dollars being a unit. Units are an indication of a numeric variable. If you see anywhere in there, if a standard deviation is given, okay? Okay, because to do problems with means, you need a standard deviation of your sample. If a standard deviation is given, then it's a problem with means, okay? Then it is a numeric variable. Okay. The other things, confidence intervals versus hypothesis test. Obviously, if it's a hypothesis test, it'll talk about hypotheses and p-values, right? Hypothesis tests will have hypotheses and p-values, okay? You do not have p-values for confidence intervals, okay? If anywhere in the problem it talks about a p-value, hypothesis test, okay? As far as confidence interval, you're looking either for the word confidence or the word interval. I mean, it sounds obvious, but if you see confidence level, it's a confidence interval, right? If you see interval somewhere in there, it's a confidence interval, okay? I think that part will be clear. But, sometimes, students see the word p-value, but then they start doing a confidence interval. Don't do that, okay? One sample versus two sample, just, you got to read. If you see how many sample sizes you can identify. Each sample requires an n. If you can only identify one sample, if you can only identify one n, then it's not going to be a two-sample problem. All right. We'll see you guys on Wednesday. We'll talk more, and good luck.